So in this session, we are going to just start our revision from Mosfet. As we discussed already, we have started from bipolar junction transistor. Then we saw in BJT, we have seen the DC analysis and the AC analysis. And I clearly explained how to play with the DC and the AC circuits when it is given in the exam. And what are the types of questions will be usually asked. Everything we have been concluded about bipolar junction transistor. It is done. Next, we will started with the MOSFET. When we were discussing about MOSFET, I have just given the introduction. We were started discussing about the basic difference between MOSFET versus BJT. This is what we were discussed in the last class. Now what we are going to do now, we are going to start from where we left. Like we are going to discuss about the various types of symbolic representations of MOSFET. From there, I will be deriving all the formulas. As I told, it will be operated in two different types of regions and they are having different set of currents. Everything we are going to discuss one by one. So let me start from the beginning. As we are observing, usually MOSFET means we have seen metal oxide semiconductor field effect transistor. So since it is having the effect of field, now, if you observe, based on this, it is having so many types of varieties, representations of this symbol. First one, if you are observing the MOSFET, it can be represented as the name is enhancement type, and the second one is depletion type of MOSFET. Now, the first one is the basic enhancement insulated gate MOSFET, represented as basic enhancement type of gate, can be represented as basic enhancement enhancement basic enhancement type gate will be represented as. So there are so many symbolical representations. I will tell one by one because that is they are very important in the examinations point of view. They will ask the questions from this. Okay. First, I will give basic enhancement. I am considering N channel MOSFET. So there are two types of channel formation. One is N channel and another one is P channel MOSFET. So let's start from here. Enhancement type, basic enhancement type and N-channel MOSFET will be represented as it is having a certain symbolical representation. It is having a three terminals. So those three terminals will be represented like this. So this is one type of representation. Here the most important thing is the direction of the current. That is very important. So when we are observing the basic N-channel MOSFET here, the direction of the current. So this is source and sorry, wait, I will start from here. So this is gate and the top down current direction is going towards it should go towards a drain terminal and this is going to be your source terminal. So current is going from source to drain here in case of basic enhancement and channel MOSFET. Now the basic enhancement P channel MOSFET. If I am having P channel, then same symbol we can take, but there is a small difference. What difference? Let's see. That is also represented in the same pattern, but you can observe there is a slight variation. Slight variation is in terms of direction of the current only. So we are observing first one, I said that is N channel MOSFET. If you want to consider it as a P channel MOSFET, what you have to do? Just we will have to reverse the direction of the current. So the P channel MOSFET is carrying the direction of the current in the opposite direction to the original one. That's it, sir. So this is the basic difference between N channel and P channel MOSFET. And the next one is now without bulky semiconductor. Without bulky semiconductor, how to represent the MOSFET symbols? There are other way. Same N channel and P channel can also be represented. Same. Again, I will be giving the other way of representations for N channel and P channel MOSFET. But this time, I am saying you cannot observe the bulky nature of semiconductor. The symbolic representation. The second one is there is no bulky semiconductor. There is no bulky semiconductor. That is what you must remember about the second symbolic representation. There is no bulky semiconductor. Okay. So there is no bulky semiconductor. That's the here also same thing. You can keep there is no bulky semiconductor. In this case, how should I, what is the symbolic representation? This symbolic representation is the most important one, and of course you can observe that in the examinations also repeatedly questions should be framed here. So the first one is N channel as we are starting. Even in the examinations also this symbol will be often used standardly. So this one represented like this. So here also this will be represented as there is no bulky semiconductor nature in this. What will be the direction of current? As usual, when we are observing the N channel MOSFET, the current will be going from drain to source, and this will be the gate terminal, this will be the direction of current. For P channel MOSFET, the direction of the current will get reversed since this is drain, source, and this is going to be gate. So it is similar to NPN and PNP transistor. When we are observing the NPN and PNP transistor, in case of NPN transistor, just recollect the basics once. When I was discussing about NPN transistor, what I told you all know this: collector, base, emitter. Now, in case of NPN transistor, collector current is entering towards the circuit, inside the circuit. Base current is entering inside the circuit. Emitter current is going away. This is for NPN transistor. If we are discussing about a PNP transistor, if I am reversing this process, for a PNP transistor, the direction of the current across the emitted terminal will get reversed. It means from base current will be going outside of the circuit, from collector current is going outside of the circuit, only through emitter current is entering inside of the circuit. So this is called PNP transistor. Whereas in NPN transistor, we will be measuring the voltage from base to emitter. From PNP transistor, for PNP we will be going from emitter to base. Here we are measuring the voltage from collector to emitter. Here we will be measuring the voltage from emitter to collector. Everything is opposite. So the conclusion is, and here we know, here in NPN transistor we will have a back-to-back diode connection representation internally like this. In case of PNP transistor, this case is volta. The diode will be like this since the diode direction will be opposite to each other. But if you observe, the representation is completely different. PNP and NPN are opposite to each other even in structure wise also. Everything is different. Same thing, if you are observing the MOSFET, here also we are having three terminals: gate, source, drain, and the gate, drain, source again here. If you observe in N channel MOSFET, current is going away from the source. Here, current is entering towards the source. Current direction will be represented only at the source terminal. Remember, it will be represented only at the source terminal. So symbol, this name will not be given in the exam. They will give only symbol. You will have to identify which is drain, which is source, which is gate terminal. After that, you will have to identify whether it is N channel MOSFET or it is a P channel MOSFET. This one also you only have to identify based on the direction of the current. If the current is going out away from the circuit, then that is called N channel. If it is entering into the circuit, then that is called P channel MOSFET. That is the another most symbolical representation of the N channel and the P channel. The both are enhancement MOSFET only. One more thing, what I would like to conclude here is these both are enhancement type of MOSFET. We have seen there are two types. One is enhancement type, and the another one is depletion type of MOSFET is there. I will give that now. So this is enhancement type representation, and the of course this is the most important one amongst all other type of representations of the MOSFET switches. This is the most important one. Now let us enter into the depletion mode. So the same one, suppose if you are in depletion mode, how should I represent? So that is the symbolical representation, but we are in depletion mode. So when the moment we are discussing about it, depletion mode, as usual, even depletion mode also we have two regions. One is N channel region, and another one is that is N channel MOSFET, and the another one is P channel MOSFET. Sir, how should I represent this N channel and P channel once again here? When we are observing that it is represented as it is called depletion MOSFET, its symbolical representation is going to be, I will show you now. So one second. Okay. So let us consider same way. it will be represented like this. Okay, perfect. So we will have 3 lines here. This will be taken here. So we have to take one more line from here. Just observe the difference. So these two things are attached. Yes. Similarly here, let me take one more line. Yes, this one. These two will be attached together. And here, this one taken away. This will be going here. Finish. So what will be the direction of the current? Our next target is the most important part is the crucial part is of course observing the direction of the current. In case of p channel depletion MOSFET, the center body is carrying the current. If it is given, yeah, it is carrying the current. I said it is p channel, no? Yeah, it is carrying the current from this source, from this body. It is coming out. Whereas this is, I am saying this is what? P channel. For P channel, as usual, this is source and this is drain and this is gate. Sir, you can observe the difference. In enhancement type, the symbolic representation is different. So in depletion type, this representation will be different. So in depletion type, current will be entering inside. So this is going to be drain. This is going to be source. As usual, this is going to be gate. So this is N channel MOSFET. But both are depletion modes. Both are in depletion mode. Fine. So these things are completed now. What is our next target? So the next target that we are going to keep now is, see, what is the most important thing that you must keep it in your mind is, in the examination, a big confusion will come regarding the direction of the current. Because what doubt will come is, as we are observing that in the symbolical representation, whenever we are discussing about P channel and N channel, enhancement type MOSFET, if you are discussing about enhancement type MOSFET and depletion type of MOSFET, whenever we are talking about P channel and the N channel, what is the basic difference that you must observe here is, in case of N channel MOSFET, if you observe the enhancement type, see that the direction of the current is going outside. Whereas here, if you observe the N channel MOSFET, the direction of the current, with the body it is going inside. There is an internal operation, sir. There is an internal operation. So what you must understand is, you will be thinking that here also current is going outside. Here also whatever wherever the current is going outside, that is called N channel MOSFET. No, that thing you must keep it in your mind. In body, the direction of the current is opposite to the original representation. When body is given, through body, if you are considering the current, that is opposite to the actual representation. Hope you understand. That is all about symbolic representation. I have given all required things. Now let us discuss about the current. So when we are discussing about the current expression, rest of everything as we have discussed in the last class, I will start from the beginning. So we know the MOSFET. First step, we will have to base in the examination point of view. The first one is, you will have to always keep your attention with the gate to source voltage. Since we observed that the MOSFET is having 3 terminals, I am taking N channel MOSFET, enhancement type of course. So this is having 3 terminals, drain, source, gate. Now the voltage that we are measuring between gate to source, we can call it as VGS, and the voltage that we are measuring between drain to source, that we are calling it as drain to source voltage. And one more voltage will be given, that is called the threshold voltage. This voltage, it is the minimum voltage required to switch on the MOSFET. So the condition to switch on the MOSFET is, the gate to source voltage that we are injecting here, this voltage must be greater than the value of threshold voltage to switch on the MOSFET. If this condition is satisfied, then your MOSFET will switch on. Once your MOSFET will switch on, then there's a chances it will enter into two different regions. Either it may be operated in ohmic region, as we have seen in the last class. Either it can be operated in ohmic region or triode region. It is also called triode region, or it can also be operated in saturation region. The another region is, it can also be operated in saturation region. So in which region we are going to operate our MOSFET now? That is the next question. How should I identify in which region our MOSFET is under operation? So let us see. To know that, let me guide you. Let us see. The first step, you will have to cross check. As I told you, you will have to cross check whether the value of VGS is greater than VT or not. And remember, VGS can be written as, that is nothing but the difference between gate voltage and the source voltage only. First check this. Once this condition is satisfied, then enter into the second condition. Calculate the value of drain to source voltage. Find the value of VD minus VS. Once you find this, then find the value of VGS minus VT. After finding the value of VGS minus VT and VDS, your next task is, now you can cross-examine whether the value of VDS is less than VGS minus VT. For N-channel MOSFET, I am writing all these relations. As I told you, I am taking N-channel MOSFET as the reference. Check whether this condition is satisfied or not, or the another expected condition is VDS can become greater than or equal to VGS minus VT. Now, if the MOSFET is satisfied, first it should satisfy this condition, VGS to be greater than VT to turn on. Once it is turned on, then if it is satisfying this condition, VDS less than VGS minus VT, then your MOSFET is in triode or ohmic region. It is in triode or ohmic region. That's it. Suppose if your MOSFET satisfies the second condition, VDS greater than or equal to VGS minus VT, then your MOSFET is entered into saturation region. Your MOSFET is entered into saturation region. That's it. Now, based on these two different regions, we will have a direct current formula. I am not going to derive everything, sir. I am giving direct formula. So, empirical formula is there for MOSFET. What is the standard formula that we are going to use for the calculation of drain current? Okay, I will tell you. I am dealing with the N-channel MOSFET again and again. I am repeating. Later, I will tell you the difference between the N-channel MOSFET and the P-channel MOSFET. But for time being, you will have to understand that we are not writing the common formula for both the N-channel and the P-channel MOSFET. The one that I am writing now is not the common one. This is only for N-channel MOSFET. Later, I will tell you how you can use this formula for P-channel MOSFET also with a slight modification. That I will help you. Don't worry. As of now, focus on N-channel MOSFET. Now, what I am saying is, for N-channel MOSFET, if it is given that the channel is N-channel, then what is the formula for drain current? The same formula you can use for P-channel. There will be slight difference. I will tell you later. Drain current is going to be, the general formula is mu n C ox W by L into, in bracket, the formula is going to be VGS minus VT into VDS by 2. 1 second. Yeah. Sorry. VDS minus VDS square by 2. That is the correct relation. This is the standard formula that we are going to use to calculate the value of drain current. Sir, is this formula is applicable for both region? Can we use this formula for both triode region and saturation region? If you are asking that question, then our answer is no. This formula is not the generalized formula for both region. This formula is applicable only for triode region or ohmic region. So you can use this formula. And what you must remember is, I will tell you, sir, this factor will be clearly given in the exam. Don't worry. Don't worry about the given permeability. You might be thinking about the given permeability and capacitance of the oxide and W by L, that is width to width by length ratio. Everything will be considered as a constant K. This will be given directly in the examination. You no need to be bothered about this value. Okay, you have to focus on only the calculation, simple calculations. So I will be treating it as K. Then the above formula can be rewritten as drain current equal to K into, inside the bracket I can rewrite it as VGS minus VT into VDS minus VDS square by 2. That is the formula. Okay, so this is the formula that you have to use for triode region. Now, when we are entering into saturation region, what will happen, sir? I will tell you. When we are entering into saturation region, then the formula will be different. Nothing. We know in saturation region, the minimum expected voltage is VGS minus VT will become equal to VDS. That is the minimum point. Further, VDS will be greater than VGS minus VT. We know that. When I am replacing VGS minus VT by VDS, then what will happen here? the above drain current can be written as K times of, I can rewrite this one as VDS into VDS will become VDS square minus VDS square by 2. What will happen, sir? This will become K by 2 into VDS square. This is what you will be getting here. This can be rewritten as once again K upon 2 into VGS minus VT whole square. This is the final answer that you have to remember for the calculation of drain current. Understood, sir? Don't forget. This is one of the most important formula that you must remember. There is no option for you. You will have to memorize this. Write as many times that you want. But you will have to remember. There is no option for you. Fine, sir. So the next thing is, as I told you, in triode region you will have to use the above one, and in saturation region we will have to use the below formula. Now from this formula, there are certain questions to be framed. First, what they will ask is, in the triode region itself, you will be requested to calculate the value of transconductance. I will tell you how to calculate the value of transconductance in the triode region. The formula to explore the value of transconductance. The first question. In triode region, you will be requested to calculate the value of transconductance. So the transconductance is nothing but GM. GM is just a transconductance. How should I explore the value of this transconductance, sir? In order to explore this transconductance, we will have to measure. See, first of all, conductance is the reciprocal of resistance. Will you agree with me? You must agree with me. Conductance is the reciprocal of resistance. For resistance, we will be taking the ratio as R equal to V by I. Then for the conductance, we have to reverse this I by V, we have to take yes. And the next thing is, transconductance is nothing but the relation between drain current versus gate to source voltage. What we are doing is, we will be taking the ratio just to differentiate the drain current with respect to gate to source voltage. At this point of time, you can assume that the value of drain to source voltage will going to be constant. This is the formula to obtain the value of transconductance in triode region. So when Mosfet is working in the triode region, usually it is called a linear region. People will be calling. See, that is one more question here. While calculating this, I will tell you. This is a triode region. When your Mosfet will be operated in triode region, it will be working as you can operate it is working as a resistor. You can consider it as a resistor. Mosfet is working as a resistor. That is another most one, because it is linear property. The ratio between the voltage and the current everywhere will become constant. Because of this, you can operate the MOSFET as a resistor when you are operating it in triode region. Remember that in triode region or ohmic region, MOSFET can be treated or it is working as a resistor. That is one more question. And next thing, if it is asked, if you are requested to calculate the value of transconductance, just to differentiate the expression with respect to what I can say VGS. Where is the value of formula, sir? Drain current for triode region, I have already given here. This is the given one. In this expression, if you are differentiating the above expression with respect to, I am going to differentiate this diode current with respect to VGS, with respect to gate to source voltage. If we are doing that, what did you give, sir? Mu n C ox omega by L, that is W by L, all are constant. So this way you no need to touch this. Differentiate the integral parameter. If you are differentiating it, see absolutely what will happen. So this term will be 0 because there is no VGS. In the first term, if you are differentiating VGS, that will become 1. 1 into VDS will come outside. Yes, no, sir. VGS minus VT into VDS. So VDS will come outside. This is nothing but transconductance formula in triode region. If they are asking you to calculate the value of transconductance, just observe VDS and the value of K will be given. Directly take and multiply with VDS. That will give you the value of final answer in one step. But you must remember how to calculate the terms. What are the things that I am discussing here that you must remember in your mind. Okay. Now let us enter into saturation region. Why I am mentioning intensely? Why I am mentioning again and again? We are doing this in triode region, sir. Because in the examination, transconductance usually it can be calculated in both region. In saturation region also same question will be framed. you will be requested to calculate the transconductance. But in saturation region, the formula is different. No? Drain current formula is different. So there the value of the transconductance also will be different. This formula is applicable only for triode region. Okay. Next, let us enter into saturation region. When we are discussing about saturation region, in saturation region we know the minimum expected value. First thing, the minimum expected value of drain to source voltage is minimum expected value is it is at least equal to VGS minus VT. And in other places, in all other cases, VDS should be greater than VGS minus VT. So this is the minimum expected point is what I would like to conclude from this. What I can say, the drain current in saturation region will be equal to, we have seen mu n C ox W by L. This is what I was considering it as K whole divided by 2. That is the constant here factor. And inside the bracket, what we can put VGS minus VT whole square or VDS square. We know VGS minus VT and VDS both are equal since we have seen that. Now this is the formula that I know, sir. In saturation region conditions also we know everything we know, sir. The next condition is, the next one we have to remember here is how should I perform? How should I calculate the value of transconductance here? What is the formula for transconductance? I told you this is just to differentiate the drain current with respect to what? Gate to source voltage. So you have to repeat the same process again. So just to differentiate with respect to gate to source voltage. The above expression, if you are differentiating, you will be getting mu n C ox W by L. This ratio, everything will be given in the exam. Don't worry, don't think too much about it, sir. You are writing so many unknown factors. How should I calculate? No need to feel, no need to worry about it, okay? Because everything will be given in the question. So here I am just differentiating. If you are differentiating VGS minus VT whole square, this will become 2 times of VGS minus VT. That's it, sir. So here this 2 will going to cancel. So this formula will become mu n C ox W by L into VGS minus VT is the formula to obtain the value of transconductance in saturation region. Now you can cross examine. Sir, it is almost similar to the previous one. But what it is different is here you can replace this VGS minus VT equal to VDS. But there that is not the case. You will have to calculate VDS separately. Because what we saw, the value of VDS in linear region less than VGS minus VT, that is the difference. Formula wise both are same, but in calculation wise they are different. Here, if you know VGS minus VT, you can replace it by VDS. But in linear region, that is not possible. You will have to explore VDS separately. This relation is not valid there. Understood, sir? That's it. So now we know the formula to calculate, so to explore the value of transconductance. Now from this, what I can say is, if you are re-observing it again, 1 second, wait. One more time I will tell you, sorry. One more way I will tell you. What we saw here is, we know drain current in saturation region that can be written as mu n C ox W by L upon 2. Here it is VGS minus VT whole square. Correct answer. Now, if we are comparing this resultant term with the above term, what is the basic difference that you can find? If I am just finding the above one, here the factor 2 is missing and the square factor is missing. So what I am going to do here is, I am just interconnecting this above and the below. Or else you can do one thing. See, this expression can be rewritten as 1 by 2 into mu n C ox W by L 1 VGS minus VT. Break this square into 2 off. So we can write it as VGS minus VT into VGS minus VT. Can I write like this? If you are writing like that, with 1 VGS minus VT, what I can say is, I can directly substitute transconductance into VGS minus VT. Can I write like this, sir? Yeah, we can write. Nothing is wrong in this. Now, from this, what I can conclude further, what I would like to proceed here is, the transconductance can also be written as 2 times of drain current should be given in saturation region. If it is given, divided by VGS minus VT. So, the another way of directly bringing the answer for transconductance is, if saturation current, drain current, if the drain current in saturation region is given in the question examination directly, and the value of VGS minus VT also given, then what you can do is you can directly calculate the value of transconductance by taking the ratio between 2 times of drain current in saturation region divided by VGS minus VT. That is another most important formula. These formulas are applicable in saturation region, sir. That's why here I am highlighting that we are in saturation region. Don't forget what are the things that we are doing here, because all are very important. Absolutely, you cannot ignore that. Okay, fine, sir. Now the next thing is, so I have given all sufficient thing whatever that are required in our examination point of view. Okay, so all you have to do is remembering everything in a proper way. That is one way of finding this answer. And the alternative way, see, the transconductance can also be written in many ways. From this expression, if you are keeping VGS minus VT one side and pass all other terms in the other side, or otherwise what you can do, that just to take square root on both sides, again you can resubstitute whatever the data that they are giving in the examination. Now based on the data that they are giving, what I can say is I will write the formula here. You will be cross examined. This transconductance I am writing, it can also be rewritten as twice of mu n C ox W by L, the length, that is width to length ratio. We can also write this into ID. Directly I can consider it as drain current ID, and along that I will be putting square root. Just cross examine how it came, sir. A small step. You can cross examine with the previous one. You will be getting this answer. Nothing I did, a small changes I did. If you are comparing the previous one with the present one, here itself you can conclude that what you can bring the conclusion what type of changes that I would have made here. Okay, so that is the another way. If drain current alone given and mu and C of W by M ratio is given, then directly you can explore the value of transconductance by using this formula. What is the formula, sir? 2 times of mu and C of W by L into ID, that is in saturation current, that is ID saturation current, whole power 1 by 2. That is also the other formula to calculate the value of drain to saturation current. Okay, so don't forget all whatever the things that they have given. So this is all type of, these are only these type of questions will be asked in the examinations. Now I will take some circuits and I will show you usually what type of analysis we will be doing in the examination. There are certain standard configurations are there, but usually I never recommend you to go with the standard configurations and memorize the formula. Go with the general procedure. What they will do, they will give some set of circuits. Name of the circuit is, we are calling it as pixel bias configuration. There is a name for this, I can tell, but I am just showing you the way how to solve whenever the questions will be framed in the exam. Okay, if a question will be given like this, they will give all voltages. So gate voltage will be given and the drain voltage will be given. That is drain. VDD means common drain voltage. That is supply voltage. And this is VS. This is VD and C. This resistor. It is in with. It is connected in drain terminal. This is connected in source terminal. Now, if you observe the present circuit, if you are requested to cross-check the circuit, what you have to do? Here, you can apply only one and only KVL. Just from this top, it is a source. This can be represented like this, plus minus. We can consider it as VDD. Just to apply KVL, I am writing like this. Top plus, bottom minus. For the resistor, current is coming in the downward direction. Mark the polarity for resistor. If I am marking the polarity, since the current in downward direction, entering point is plus, leaving points are minus. And the current that is coming into the network is called ID, drain current. Now just apply KVL, sir. Just apply KVL. If you are applying KVL here, this will give you minus VDD plus ID into RD plus ID into RS. One more term I left. What is that? The voltage drop across the drain to source terminal. So we will have to consider drain to source voltage VDS equal to 0. And the next thing what you must carefully understand is VDD is different, VD is different. VD is the terminal voltage of the Mosfet. What mistake I made? Symbol representation. Sorry. Put one more line here. So the thing is, everything will be clearly given, but you should remember that the terminals of the MOSFET can be separately considered as VD, VG, VS, everything. Some of you will be considering that this is Vs. You will be treating like that. That is wrong. You should not take this is Vs. Where is Vs? Terminal of the MOSFET only can be treated as Vs. Understood, sir? That's it. Now, after writing the KVL expression, now just to focus on what are the data that were given in the question. Substitute. Definitely RD will be given, RS will be given, VDS they may not give, they will not give, but VDD will be given. So by solving this expression, you can bring one relation between VD versus VDS. Okay, you can bring the relation. Now, what is the other expression? Based on the region of operation. If it is in ohmic region, if it is in ohmic region, then the another formula is drain current can also be written as mu n C ox W by L into, in bracket, what I can say is VGS minus VT into VDS minus VDS square by 2. We know this formula. So we know this formula. From this, you can bring one more relation. See, ultimately the data will be given. Key points will be given. Threshold voltage definitely given. Either they will give VT or VTH. Don't get confusion. That is threshold voltage. Minimum amount of cutting voltage required to turn on the MOSFET. That will be given in the exam. Directly you can take and VGS. Try solving problems. You will get idea. VGS you will have to calculate. By from this equation, mu and CR, it will be every time it will be given in the exam. You don't need to solve these things. It will be directly given in the exam. You can substitute the data and from here you can form one more equation. Already we have another equation. Try to solve this to figure out the value of drain current, or if they are asking drain to source voltage. Whatever the statements that they are asking, you will have only two choices. One is current expression, another one is the KVL expression from the circuit. It doesn't matter what type of circuit they are giving. The beauty of the MOSFET is from the gate there will be no current, that is zero. So don't worry about it. Even they are giving some resistor at the gate terminal, don't focus on it, because we are very well know that this body is insulated fully. Here current will never ever enter into the MOSFET, so you can assume that current is always zero. In that case, you will have only one KVL equation. Whereas in BJT, in bipolar junction transistor, we can form two KVL. One is from base to emitter, another one is from collector to emitter. So by solving those two KVL equation, we are identifying all unknown data that they are asking in the question. Here also we are bringing two equations, one equation from the circuit, another equation from the formula. These two things you must register it in your mind. So that is of course a little bit most important one. Same thing, if the MOSFET is in saturation region, suppose it is given that the MOSFET is in saturation region, then instead of using this current, don't use this. If it is in saturation region, we know the value of drain current can be written as, repeat with me, Cn, mu n, C ox, W by L by 2, what do you have to write, sir? In bracket, VGS minus VT, so this is drain current, sir, into whole square. This is what we found. So we know the drain current is saturation region. But take that current and once again solve, observe the diagram, apply KVL, form one more equation, solve the two equations and try to figure out the answer. Finish. So you will be able to solve almost 95% of the questions from the circuit diagram whenever they are asking. Only these two formation of equations you should clearly study. That's it. It will be enough to solve all type of questions, whatever that is asked in the exam. Finished, sir? Done. Now we are going to enter into the another zone. I will tell you at last. I will tell you the difference. As of now, we are entering into the next part. This is so far whatever the conclusions that I brought here. These all are called DC analysis of MOSFET. I will solve some example questions after completing DC AC analysis. Okay, such that you will get the idea how to solve it. It's a kind of revision class only. You'll have to understand. That's why I'm not giving in-depth explanation for any of the term. But whatever the things that I am covering, that will be sufficient to crack all the questions. All you have to do is practicing is very important. Just by observing the lecture, making the notes may not be help you to crack the question. You will have to practice. Fine, sir. Let us continue. The other one is AC analysis. Let's start with the AC analysis. First, I will draw the AC equivalent circuit of MOSFET. After that, we will come to know what is the difference between BJT versus MOSFET AC equivalent circuit. So it's very simple symbolic representations. I will draw it for N-channel MOSFET. I will tell you what changes we will have to keep if we are doing the same thing for P-channel MOSFET. As usual, from the beginning, I am doing everything for N-channel MOSFET. So here also, let's take N-channel. At last, I will tell you the difference. If you are doing the same thing with the P-channel MOSFET, what you have to do? A small variations will be there that you can directly note it down at last. Sir, sorry, AC analysis, first draw the MOSFET equivalent circuit. For N-channel MOSFET, I am going with the as usual N-channel enhancement type mode, and it is having three terminals. So there are three terminals. What are the names, sir? This is called a gate terminal. This is called a drain terminal. This is called a source terminal. What can be the AC equivalent circuit? Similar way, in bipolar junction transistor also I did the same. Just to go back to the previous lectures and see in bipolar junction transistor how I made this AC equivalent representation of the BJT symbol. Same thing we are going to do here also. What we are going to do, sir? It is very simple. See, first start from the gate. Draw a straight line and leave a gap. What gap we are leaving? I will tell you later. Just to leave a simple gap and draw a straight line. Just to draw this pattern. After drawing this, once again, go back here, connect one source, and of course, this is also going to be a current source, but it is typically voltage controlled current source. I will tell you this one also, don't worry. Let's continue. On the output terminal, or I can say in the drain terminal, we will also have a resistance. We are considering it as RD or RDS or R naught. So this will be directly connected with the ground. That is drain to source resistance or output resistance. We will be considering as output. One second. Since different types of configurations will be given. If the source is not connected to the ground, then you have to connect it here. Wait, I will tell you. Okay, done. So let us connect here. I will go with the without confusion. I will draw. Now expand one more line here. This is going to be a source terminal. Fine, sir. Now, this is the AC equivalent. Only one model. In BJT, I have given three models, but here only one model. First one is this is gate terminal, this is source terminal, and of course, this is going to be your drain terminal. Totally, we have three terminals. And here, on the gate to source side, you will have a voltage is called gate to source voltage VGS. And this can be represented as transconductance GM into gate to source voltage VGS. Understood, sir? So this is the complete representation. And if you are asking me why I have open circuited this terminal, what is the reason behind of this? We know through the gate terminal current will not come, sir. So in order to say that is a open circuit, we are always open circuiting this terminal. It is very easy, sir. AC analysis of MOSFET is very easy. Because one side is already kept open, only one side will be closed. You can easily observe it. Suppose if there is any questions will be framed in the exam, you can easily analyze it. Okay, so draw it one more time for your understanding purpose. I am doing this. How will you draw, sir? If a symbol will be given, what you have to do? First name it. Drain, source, gate. Next step. Draw the AC equivalent circuit. Start from gate terminal, draw a straight line, then leave a gap again, then draw a straight line, then go to source terminal and the drain terminal. Just go there. Take one more pattern. So here what we are going to do, sir? We are just connect one current source. After that, extend this line. We are also going to connect one more resistor here, and that resistor will be treating as output resistance, and of course we will be considering it as drain to source resistor, exactly if you want me to say this. After that, and this is going to be GM into VGS, we have seen this is called transconductance into drain to source voltage. Here what we have said plus minus, I can say gate to source voltage, and the effect of gate current will be 0 ampere, yes, and here a little bit extension is required for source terminal. All put together totally we have three terminals, sir. Yes. So the terminals are, we can rename it as gate terminal, source terminal, and of course this is going to be collector terminal. That's it. Understood, sir? This is all how we are redrawing the AC symbol of Mosfet. As I told, this is for N channel MOSFET, so we are doing VGS and everything I have written here. Yes. If we are doing the same thing for P channel MOSFET, all you have to do is only one thing. In place of VGS, just keep VSG. That's it. In place of VGS, just keep. I said now this is a simple reverse process. That's it. Nothing will happen beyond that. You can keep the same circuit. All we have to do is renaming it. Whatever the things that we are writing, that is we have to rename them. That's it. Okay. And the next one more thing I would like to conclude. The drain to source resistance usually will not be given in the exam while solving the problem. Still we can approximate it. I will tell you. At the same time, we cannot give assurity. Usually this value is it is very high. This value is very high. So if it is very high, then what conclusion we can give here is the value of, if the value of R naught or RDS is not given, then you can assume it is infinity. If you are assuming it is infinity, then the above circuit will be redraw as gate terminal will be there as usual, gate to source, draw a straight pattern, then connect only a current source. That's it. Just extend this line and write this value is Gm into VGS and don't consider that resistor, only keep this terminal. Finish. So this is going to be source terminal, that is your drain terminal, this will be your gate terminal. Between gate to source voltage you will be having gate to source voltage, but current will not be there since it is what we have been insulated the gate terminal. That's it, that is the equivalent circuit. So it is very easy. See how easy it is now. Directly, sometimes what will happen, questions will be asked directly in the examination. Same type of analysis we can perform, sir, as it is given. Whatever the things that we have done for bipolar junction transistor, same thing you can perform here also. What I would like to mean, I would like to say, for example, suppose if a general circuit or if any circuit will be given, and if they are requesting us to calculate the value of the resistor, I will tell you, see, input in AC, what type of questions will be framed in the exam. As usual, they will ask you to calculate the value of output, voltage gain, current gain. They will, output gain, voltage gain. They will ask impedance. They will ask input impedance, and they will ask output impedance. Only these three type of questions will be asked. Why they will not ask the current gain? Why I have stopped when the moment I said current gain, I said sorry, because we know we are in MOSFET. In MOSFET, there is no current. This current is 0 ampere, sir. You cannot take this. That's why current gain we are not usually calculating in MOSFET. But we are calculating the value of voltage gain. Of course, we can calculate the value of output resistance. Rest of process will be doing. So what they will talk is, they will talk about voltage gain, they will talk about input impedance, they will talk about output impedance, everything they will do. Rarely, if the source resistance will be given, source current. If it is possible to calculate the source current, if they are calculating it some other side, then they will ask current gain. So most of the time, only three type of questions will be framed. One is voltage gain they will ask, or otherwise they will ask input impedance, or otherwise they will ask you, they will request you to calculate the value of output impedance. So these are the three most important repeatedly asked questions from AC analysis of MOSFET. Okay, sir. I will show you some of the example how to perform when a general diagram will be given, such that you can get clear idea about AC analysis of MOSFET. Okay. Suppose we will take the same circuit that otherwise I will take some other type also. I will show you how to perform this. For example, if a circuit will be given like this, okay, and here also one more resistor will be given, and they are considering this is going to be drain resistor, this is considered should be, this is going to be a source resistor, and what we are doing here, one second. Ah, so this is, here we are giving VDD, and at this point we are going to give gate voltage, so I am considering it as VG, and of course this is going to be VGS, gate to source voltage, and this terminal is source terminal. I am repeating, this terminal is your drain terminal. This, suppose let me connect it with the ground. And what we are going to give is, we are giving the input voltage on this side. So I am giving a source resistance, I am going to consider Let us assume there is a source resistor and it is of course connected to input voltage Vn. This is going to be input voltage. Now what we have to perform is we are going to perform AC analysis. Let us assume that the value of RD is given as 2 kilo ohm and take the value of RS also 2 kilo ohm and take the value of source equal to 1 kilo ohm. Let us assume it is too much. I know that is very high value. I am just taking. Sir, one more thing, while measuring the output, usually here also they will give capacitor everywhere. Wherever they are giving the capacitor while doing the analysis, just short circuit the capacitors. Okay, simply short circuit the capacitor. No need to do any other things beyond that. Okay, so here also they will frame the question with the capacitor or without capacitor. If they are connecting the capacitor, no, just to short circuit it. I will show you with the capacitor. Later you will understand this. So this is going to be across the source I am connecting the capacitor. This is at the drain terminal we are connecting capacitor. This is going to be output voltage. Of course, here also capacitor will be given at the gated terminal. What you have to do is just a short circuit by performing AC analysis. Shall we start doing this? First, to learn how to draw the equivalent circuit. That is the most important step. For that, only take this symbol. Don't draw any other things. First, only take this symbol. For gate, we will have to draw a line. Then leave a gap. Then draw a line. Then again, consider this. This is going to be GM into VGS. In this question, output resistance regarding R naught or drain to source resistance information is not given. So assume that value is infinity. Just open circuit it. This is going to be till drain terminal we have drawn. So here I am expanding it till source terminal. This is the symbolical representation. Now just to name them. I can name these three people as this is going to be our gate terminal and this is going to be our source terminal and of course this will be our drain terminal. Now focus. At the gate terminal this capacitor will be short circuited and we have a source resistance and the input voltage. Let's see. So what I have to do is I will have to reattach the given data. Let us consider a source resistance. Along with that we will be having a voltage source here and this is considered as this is going to be input voltage Vn. Okay, sir. So that is what you have to do. After that, the next step what you are going to do here is source terminal. Let us focus on source terminal. On the source terminal, see there is a capacitor. That capacitor that will be short circuited. If the capacitor is short circuited, then current will always choose low resistance path. Entire current will be diverted through the short circuit. So this RS is useless now. Whenever a bypass capacitor will be connected across the source resistor, then it is not possible for us to consider the effect of the source resistor when we are performing AC analysis. Remember that. In DC analysis, capacitor will be open circuited. While performing DC analysis, these capacitors will be open circuited, sir. Okay, let's continue. Since because of the presence of capacitor, there is a short circuit, the source terminal will be directly connected to the ground. Next thing is, let me tell you, see, from the drain terminal, a current is coming that is called a drain current. It can also be considered as GM into VGS. So this current will be coming here. After reaching this junction, we know through the gate there is no possible for current here. So this current will not be present. So here I know this current will be 0. So this drain current will come here. After reaching this, it will be bypassed through this ground. There is no more other things. Now go to drain terminal. On the drain terminal, we are going to short circuit this. This capacitor will be short circuited and this drain supply voltage will be short circuited. Then what you can do is, what you can observe is, on the drain terminal, between drain and the ground, there is a resistor. You can connect it with the ground. And that resistor I will be simply treating as RD. Extend this. From here, we are going to measure the value of output voltage. Now this is the complete AC equivalent circuit for the given. If it is the complete AC equivalent circuit, how should I explore the value of gains, all the parameters? Shall we start doing that? See, first thing is, on the input side, there is no possibility for the current coming out, that is 0 ampere. Why it is 0 ampere? Because since there is only one path to send the current. But here also there is a open circuit, we have simply gate to source voltage. This is what we have here. So the thing is, since the current will be 0, then what is the voltage drop across this RS? source resistor. This is going to be 0 voltage, na sir? How it is 0? Voltage drop across the source resistor Rs equal to current flowing through the resistor into gate current into value of the resistor. Or you can also consider this resistor is your source resistance. This current that is coming out of the source is called source current, sorry, not resistor. And the current that is entering into the gate terminal is called gate current. Since source current and gate current both are same in this circuit, they are currently in series. In some questions it will be different, sir. That's why I'm not. I'm saying as of now. I'm saying whenever a current is coming out of the source, consider it as source current. If a current is entering into the gate, consider it as the gate current. In this circuit, both are in series, so gate current and the source current both are same. Since the source current is zero, zero into R will be zero. So the voltage drop across the resistor is zero. After knowing this much of information, what we are going to do, sir? Nothing. We will have to explore voltage gain. Current gain is not possible for this circuit. We will have to explore the impedance. Let's see how to calculate all these things one by one. Okay. Now the thing is first, write down the expression for input voltage. If you are writing the expression for input voltage, like I just wanted to know the KVL on the input side. Just apply one KVL at the input side. Apply KVL at the input side. If you are applying KVL, minus Vn plus Vgs equal to 0, since there is no any voltage drop across the resistance Rs, so I am not going to consider it. Sir, here across Rs voltage will be 0, so we can consider Vin equal to gate to source voltage Vgs. These both are equal for the given circuit. Treat this one as your equation number 1. Go to the output terminal once again. See that here also you can form a KVL. Just apply KVL. If you learn very well BJT, then Mosfet will be very easy. If you learn Mosfet very well, then BJT will be very easy. Both AC analysis are easy only. If you have to practice few questions at least, easy questions, small questions. That will give you a good grip on this subject. All of you are feeling that it is very tough, you are unable to attend because you are not practicing, sir. But it is very easy usually. Let's see, if you are applying KVL, first thing, see, current is going in this direction. Huh? So definitely from here we are not injecting any current. So current is not coming from there. It is going from here. So current entry point plus, leaving point is minus. This polarity, from the direction of the current we are observing some polarity, but the output polarity is different. From this I can say the output voltage V out can be written as minus drain current into drain resistance RD. Drain current can also be written as transconductance GM into gate to source voltage into RD. We very well know about this because you can observe this. I have taken from the diagram only. Drain current is here, gate to see. GM into VGS is here. Both are same, same circuit. So from this, you can observe that the output expression can be written like this. Now you know the input expression. Yes. We also know the output expression. Yes. Can you write down the output current? Yes. We can say the value of output current is going to be, see, usually output current is the one which is coming out of the circuit. Output current is the one, it should come out of the circuit. But the drain current is going inside the circuit. What I have to say? Drain current and output current both are opposite. Same way I did for BJT. Correct, no, sir? That's what I'm saying. If you are good in BJT, then Mosfet will be easy. If you are good in Mosfet, then BJT will be easy. Practice record. Fine, sir. From this, I can say I naught equal to minus ID. So the next expression, output equal to minus ID. I know the value of ID is GM into VGS. It can also be written as GM into VGS. Finish? Yeah, it is done. Now let us explore whatever the questions that they are asking, you can solve it from here. For this given circuit, first thing, we will explore the voltage gain. That is the ratio between output voltage and the input voltage. So when we are considering the output voltage, just now we have seen that can be written as minus Gm into VGS into RD. And we also explored that the value of input voltage equal to simply VGS. So VGS will get cancelled. So the value of voltage gain will become minus Gm into simply RD. Okay, so see how easy it is. For the explaining purpose, in order to let you all to understand the things properly, I am spending this many minutes. But in examination, fraction of second, 5 to 10 seconds, you can drop your answer. Finish. That will be over. So let us continue. Let me continue. So we know the output current. So we have explored the value of gate gain. Then let us explore the value of output impedance. Output impedance is nothing but the ratio between output voltage divided by output current. As we are observing, output voltage can be written as minus Gm into drain resistance RD into gate to source voltage upon. We also observed that output current equal to minus Gm into VGS. So that will be simply equal to RD. This will be your output resistance. Got it, sir? Now we know the voltage gain, we also know the output impedance. I said we can calculate one more parameter, input impedance, and current gain also possible. For the given circuit, whether the current gain is possible or not. For that, you will have to cross check the input current, sir. Input current is 0 ampere. If you are exploring current gain, it will be approaching the infinity. See there? If I am trying to calculate the current gain, output current we know, we will be taking the ratio that output current divided by input current. But what you say, output current is no problem, we know, minus Gm into VGS. What about input current, sir? That is approaching to 0. In this given circuit, there is no input current. So this will be approaching to infinity. Current gain is very high for the given circuit. That's why I did not explore that value here. Now the next one, suppose if you are trying to explore the input impedance, again there is a problem. What is the problem? Input impedance equal to, I have to take the ratio between input voltage and the input current. That is input voltage divided by input current. Since the value of input current is already approaching to what? 0, sir. So input impedance will be infinity. That's why input current is 0. On the input side of the Mosfet, we are offering infinite amount of resistor. That's why it is open circuited, sir. That's why here it is open circuited. In this question, input current and gate current both are same. Input current and gate current both are same. But in every question that is not possible. What you are trying to say? I will take one more example, don't worry. As of now, so what I will do now, we have already crossed the time. So I will tell you in what type of circuit these things will be different. Let me take one more example. Let us take voltage divider circuit. Voltage divider, some of you might be heard about it. I will just show you the circuit now. Let us assume a circuit will be given like this. Along with that, they have also given one more set of resistor here. If a circuit will be given like this, then you may expect input impedance, current gain, voltage gain, output impedance, everything you can expect for this circuit. How it is possible? I will show these things in next class. Okay, I'm just for time being, I'm just showing how it is possible. It is not general that everywhere you can say that the value of overall input, current gain is infinity. Everywhere that is not truth. Somewhere current gain will exist. Like if you are taking voltage divided circuit, that is possible. It will exist. I will show you how it is. Let me consider resistor R1, R2. This is gate terminal. You can consider that is source terminal RC, RD. Then connect it with the VDD. These both are connected with the VDD. You can consider all. Everything I have given. Now try to explore. Perform AC analysis in your free time. Tomorrow I will give answer for this question. Then you can realize how easy it is. Okay, sir. So this is all for this lecture. Rest of things we will see in the next class. Thank you all.